Welcome to The Explainer. Today, we're going to dive into a world that, well, it pretty much breaks all the rules of common sense. We're talking about quantum mechanics, and our whole journey is going to start with a single, impossible-sounding question. Let's just start with a really comforting thought from one of the guys who helped build this field, Richard Feynman. He famously said, "No one understands quantum mechanics." So look, the pressure's totally off. Our goal here isn't to walk away as experts, but just to get a handle on the central mystery that completely turned physics on its head. And to get our heads around this, we're going to tackle a riddle that seems to just break logic itself. Seriously, this one question is going to be our guide through all the weirdness that's about to come. Okay, so our investigation? It starts right at the scene of the crime, so to speak. We need to look at the evidence from probably the most famous experiment in all of modern physics, the double-slit experiment. The setup is actually beautiful in its simplicity. You've got a light source, a barrier with two little openings, and then a screen behind it so we can see where the light ends up. Sounds simple enough, right? Yeah, well, the results, they are anything but simple. Okay, so let's bring in our first suspect in this whole mystery. For a long, long time, scientists were pretty sure light behaved like a wave. Kind of like ripples spreading out in a pond. And if we cover up one slit, yeah, we get exactly what you'd expect. One bright patch of light. Same thing if we cover the other one. But, and this is where your brain starts to hurt a little, when both slits are open, you don't just get two bright bands. No way. You get this. A whole pattern of bright and dark stripes. So what on earth is going on? Well, that striped pattern, that's a classic textbook sign of waves. It's called interference. The peaks of the waves from each slit add up and make the bright spots. And here's the key. A peak from one wave can meet a trough from the other and they cancel each other out, creating a dark spot. So this perfectly explains our riddle. Case closed, right? Light has got to be a wave. Yeah, not so fast. Because the story takes this sharp, totally unexpected turn when we change just one tiny little detail in the experiment. Okay, so what if we turn the light source way, way down? I mean, so dim that it's only sending out one little packet of light energy at a time. So faint that there's only one of these things in the whole setup at any given moment. So now, instead of a faint, blurry wave, we get something totally different. The screen starts registering these little individual hits. Ping, 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 like tiny, tiny bullets hitting a target. These little particles of light are called photons. And figuring this out, by the way, is what actually won Einstein his Nobel Prize. And this is where we get to the absolute heart of the paradox. As we let these little photons hit the screen one by one by one, over time, those individual little particle dots, they build up to create the exact same wavy interference pattern we saw before. How is that possible? I mean, think about it. This makes absolutely no sense from our everyday point of view. A single photon, a single particle, should go through slit 1 or slit 2. The other slit shouldn't matter at all. But somehow, it does. Each individual photon lands in just the right spot to help build a pattern that could only exist if it was somehow aware of both paths at the same time. So what is it? Is light a wave? Or is it a particle? Well, the quantum answer is, it's stranger and honestly way more profound than either of those options. The crazy truth is, it's kind of both, and it's also kind of neither. It seems to travel through the experiment like a spread-out, interfering wave, but when it hits the screen, it always arrives as a single, tiny particle. This is what physicists call wave-particle duality, and it's a cornerstone of the quantum world. Okay, so to explain this, physicists came up with this brilliant but weird idea, the probability wave. Now, don't think of a wave in the ocean. Think more like a weather map for a hurricane. The map itself isn't the storm, right? It just shows you the probability of where the storm, or in our case, the particle, is most likely to hit. That probability map is what goes through both slits and interferes with itself. But hold on, because the mystery has one last, absolutely mind-bending twist. What happens if we actually try to peek? If we try to see which slit the particle really goes through. All right, let's do it. We'll stick a tiny little detector right at the slits. Every time a photon zips by, the detector will tell us, hey, that one went through the left, or that one went through the right. Finally, we'll get our answer. But get this. The instant you look, The second you successfully measure which path the photon took, the interference pattern completely vanishes. Poof, it's just gone. All you get are two simple bands, just like you'd expect if you're firing tiny bullets. The wave behavior is completely erased.
This implies something just staggering. In the quantum world, you're not just a passive observer. The universe itself seems to change its behavior based on whether or not you're watching. The very act of looking forces that wave of all possibilities to collapse into one single definite reality.
Okay, so if this is how reality actually works on the tiny scales, why on earth don't we see baseballs acting like waves or bullets disappearing when we're not looking at them?
Well, the truth is, everything, you, me, baseballs, has a wave nature. But the rules play out differently for the very small. With big things like bullets, opening another hole always means more bullets get through, obviously. But with something tiny like an electron, opening up a second path can, bizarrely, lead to fewer of them landing in certain spots. How weird is that?
So why the difference? It all comes down to this one ridiculously tiny number, Planck's constant. You can think of it as the secret dividing line between our big, predictable world and the weird quantum realm. For something big like a bullet, its quantum wavelength is so infinitesimally small that the weirdness just gets totally washed out. We can't detect it.
So, what does this all mean? It means the rulebook we thought the universe played by? It's completely different at the fundamental level. Reality isn't some predictable machine. It's built on probability, on potential, and on the truly strange power of just looking.
And that, finally, brings us all the way back to our impossible riddle. Adding more light can make a spot darker, because light isn't just one simple thing. It's this beautiful, bizarre union of a definite particle and an uncertain wave. And that strange fact doesn't just change physics. It really makes you wonder, what does it even mean for something to be real when no one is looking?